I said that a few times yesterday and then today that there are no possible ways of breaking the laws of physics or thermodynamics. There are no cheat codes, but I think that we might have one. And that is probably in the shape of Gibbs free energy, because it is not hydrogen, it is not carbon, it is sodium. So let's see the next presenter. It's a startup called Helios. It is going to be the Helios Cycle, decarbonized iron ore reduction through sodium looping. So done by Dr. Hanni Faran, the VP R&D, Helios. Please.
Okay, so I'm Dr. Hanni Faran. I hold a PhD in physical chemistry and over 17 years of industrial experience in energy and metal casting. And at Helios, I'm the VP R&D, responsible for the development of the technology and also scaling it up. And I will present today a breakthrough reduction of iron ore by using sodium as the reductant. And the thing is about the Helios cycle that it can address some of the challenges in the steel industry by using low-value raw material and by processing it with sodium, scalable and practical, and even recycling it afterwards can address and be implemented in both of the value chains, at the end of the value chains, both in the ore mines and the steel plants. So let's dive in. Okay. So this is the cycle. We are starting with iron ore, and we are indifferent, and I will demonstrate it in a minute, but it is indifferent to the type of feedstock. And by using sodium, we are reducing the iron ore into metallized iron. And after several separation trains, we create two clean streams. One is the iron metal, and the other stream is the sodium oxide, which by using electrochemical methodology, we are reclaiming the sodium back into the system in a closed loop manner. So this is the cycle. And why we are indifferent to the type of feedstock, meaning we can use low-grade iron ore and even waste products such as tailing and slag, and we will talk about it in the next few slides. It's because that sodium is thermodynamically selective to the reduction of the iron oxide, meaning it reducts only the iron oxide and do not touch of other composition in the material. So the energy consumption is 3 megawatt hour to 4 megawatt hour per ton, and the operational temperature is between 250 degrees Celsius to 350 degrees Celsius. And this is critical because we can implement it in the infrastructure of the industry without any significant or extreme retrofitting. So let's move on to the first example. We've conducted hundreds of experiments with different types of ores, and I will demonstrate 3 of them. So one is a low-grade ore, unbeneficiated, with an Fe total amount of 37.3%. It contains hematite and magnetite, and you can see it in the XRD analysis that these are the composition. And in the table below, you can see the results after the reduction. It's before the separation steps. I will explain later on what are the separation steps, but this is only the results of the reduction itself, meaning most of the iron oxide turned into metallic iron, and sodium oxide, of course, as a sequence after the reduction place. Silica and nacrite or sodium silicate are the byproduct, and we also can control that. I will demonstrate it afterwards. So it's important to us to understand exactly the metallization percentage of this process, and therefore we calculated the fraction of the metallic sodium compared to the Fe total in the result, in the outcome. And you can see here that because we have only metallic iron in the outcome, we are reaching almost 99% of the iron metallization, meaning we do not have any other byproducts such ferrite, for example, and we only reduct the iron oxide to iron metal. So this is a really challenging material, unbeneficiated ore, and then yet we managed to receive with high efficiency the high metallization. So now we will go to the next example, which is tailings. We use tailings, which is a low-grade iron ore, 41% only, but together with it, it is a material with high level of impurities, meaning because XRD do not share the entire story, we evaluated the elemental analysis via XRF and evaluated the phosphorus and sulfur impurities in the raw material. So this is the material that we are starting off, and we wanted to understand exactly what is the Helios cycle, or what is the reduction with sodium, what is the outcome of it. So this following slide demonstrates that again, we reached almost 99% of metallization because almost all of the iron oxide turned into metallic iron. And by ICP, we evaluated the impurities levels in the outcome, in the material itself. And we found out that the level of impurities dropped dramatically. And it's really, again, significant because we started with low-value material and turned into a high-quality iron with low amount of impurities. So this is crucial to the industry and to understand exactly what is the next step. So the third example is something that we wanted to understand if our technology can handle, slag. We took slag, EAF slag, and wanted to understand if we can extract the iron from it and reach, again, low level of impurities. So you can see here in the XRD before and after the metallization percentage. We've reached 96.9% of metallization. Most of the iron-bearing material, iron-bearing phases material, turned into an iron metal. Again, 96.9%. The Fe total in the raw material is 22.8 only. And it's really a challenging material to deal with due to the calcium silicate inside and the other compositions. So we've demonstrated 3 examples, low grade and also waste material, and conducted the metallization, the reduction in high efficiency. So in this slide, you can see our ability to manage the byproduct. You can see here 2 examples of XRD from the same ore, the same low-grade ore, and by monitoring the process parameters, different process parameters, if it's the mixing, if it's the ratio, if it's the temperature, we've managed to control the outcome after the reduction. Meaning we can control in the process if we want to reach silica at the end or sodium silicate in the end. And why is it important? It is important because by controlling this outcome, we can control the separation methodologies that we want to use. So the separation flows is, again, we are starting with the reduction results. For example, here the Fe metal, sodium oxide after the reduction, and the silica as the gang. The other impurities, in most cases, we found out that has an affinity bond to the sodium metal. And therefore, in most cases, these are the outcomes after the reduction: Fe metal, sodium oxide, and silica. So the first stage is to, by magnetic separation, separate the silica from the Fe metal and the sodium oxide. The Fe metal, in most cases, will be attached to the sodium oxide because of the nature of the reduction. And after the magnetic separation, we've conducted a chemical separation in order to create two clean streams. One is the Fe metal, and the other is the sodium oxide. And it is important to us because, again, we want to reach high purity of metallic iron, and the sodium oxide, which is essential to reclaim back in the electrochemical dissociation. So this is the separation flow. And now sodium. Sodium is the reagent, and of course it's essential both because of economics and sustainability to reclaim it back and leave it back or keep it back in the closed loop manner. You can see here the system that we are using, and it's designed in order to evaluate or to reach maximum recovery of the sodium. And you can see the small animation of the sodium metal creation from the sodium oxide. So again, after separating the Fe metal from the sodium oxide via chemical separation, we use the reclamation by electrochemical unit or electrochemical methodology. So this is just diving it a little bit about the electrochemical cell that we are using. On the cathode side, of course, there is the evaluation of the sodium metal. And on the anode side, by using sodium oxide as the reagent, which is the one that the sodium reclaimed from it, there is only oxygen in evaluation, meaning we are using so-called dry condition and not hydrogen evolution. You can see in the figure on the right that by adding the sodium oxide, which is from the separation train, we are lowering the potential. And by lowering the potential, it means, in other words, that we are at the level of voltage of the oxygen evolution. So this is the sodium looping. The final product in the Helios cycle is in a powder form. And in order to bricate it, and because it is in a powder form, we can be flexible with the outcome, with the briquetted outcome. We can use different shape, size, density, because we are starting with a iron powder. So I've talked about a little bit about the starting feedstock, which in most cases we are using, or we want to see the advantage on low-value material, low-value raw material. And by using the Helios cycle, we are reaching high quality of metallic iron and manage to reclaim back the reagents in a closed manner. So before we will move forward and I will show you our broader vision, it's important to me to emphasize that this process and this technology is inherently scalable. And why is that? It's because we are using a known methodology, a known and existing engineering methodology in the process. For example, for the reduction, we are using stir tank to reactor, and for the separation steps, we are using for the low-scale Nutsch filter and afterwards Funda filter and a continuous chemical separation. So it is a known and existing methodology. Of course, we need to accommodate it to our process, to the parameters of our process, but the essence are known in the industry already. So our currently stage is a mini pilot that we are producing hundreds of kilograms per month, and our goal, our next goal, is to the pilot scale of tons per day, and afterwards to a first-of-a-kind demonstrator that will have a capacity of 50,000 tons per year. So the initial stage is doing it in a batch mode, but parallel to the batch mode, we are also evaluating a continuous, and the leap from batch mode to continuous will relatively be with a low risk due to the kinetics and the thermodynamics of the reaction. So let's move forward to our vision. Our vision, and the key point here is that the kinetics of the reaction, as I said, is extremely fast. And because of that, our goal is not to scale up in a building size furnaces, but modular, semi-trailer size units in a size of 240 feet containers. And we can stack those units. The previous units, again, is the 50,000 ton per year. So we can stack those units into a large area to increase the capacity, and it can be implemented, as I said in the beginning, both if it's in the mine side or if it's in the close to the steel plant. And 10 years from now is to have a assembly facility that will manufacture those units and, of course, increase even further the capacity. So to summarize, we used low-value feedstock, and it can go from low-grade material, if it's hematite, magnetite, goethite, and even wustite, and also waste material, waste products such as tailing and slag. And from those material, convert it to high-quality iron metal, and with a scalable process and a relatively practical process, we can change how we think and approach raw material in the industry. So thank you very much. And we talked about collaboration, how important it is. So feel free to reach out and talk with us again. Thank you.
Thank you. Questions?
Thank you, Dr. Hanni, for your nice presentation. I have one question. So have you done any energy balance? Suppose you have a mill scale, which is high FeO content, more than 90%. You have a slag, which is 20 to 30% FeO, iron oxide. So how is the impact of energy during your process?
Yeah, so 95% of the energy is from the electrochemical process, from the process of the sodium reclamation. So this is 95% of the energy. And according to the mass balance, we are using the metallization as the first part, and the separation step. Currently, we have a loss of only 20%, but it's because we are only in the beginning of scaling up. We didn't optimize yet the operational process of the separation.
No, based on your thermodynamic calculations, so either you will reduce a high oxide material and low oxide material. What is your energy balance?
So actually, because most of the energy is due to the sodium oxide, it's really not matter because it's the outcome of the reduction step, meaning the amount of energy will go together with the amount of sodium oxide that we need to reclaim back.
Okay, thank you.
There is another question there.
Thank you very much. Very charming ideas. Yes, your electric power consumption is very reasonable. I have a simple three questions. Is the first is I am very curious about your yield output in comparison with input. And the first is my question is. Second is do you have any expected OPEX? Is the OPEX. Third is there any scale-up risk in your ideas?
So let's start with the first one.
Is
Can you repeat it again?
yield.
What
How
again?
much I can get?
The yield?
Yield.
Okay.
How much amount is the FE from the input?
Yeah, so currently the yield loss that we have is, again, as I said, it's due to the separation methodology, and it is around 20% yield loss. And not because we cannot metallize the oxide, it's because of the separation optimization, let's say. And we assume that by scaling it up, we can optimize it even further. So this is the yield. What is the second question?
Second is the expected OPEX.
OPEX, yeah.
Per ton.
Yeah, okay. So we are performing a Aspen simulation to the next scales that we are doing. And most of the price tag is regarding the CapEx itself and not OPEX. We are using a continuous sequence, and therefore the OPEX is relatively low, but it's a good question, and I can look it further in the simulation and give you an answer afterwards.
Yes. Third is the scale of risk. Is there any scale of risk?
Scale-up risks? Yeah. Well, as I see it, currently two. One is sodium reaction is highly exothermic, so we need to monitor the temperature in order to avoid byproducts. So by monitoring the temperature, we can avoid, again, the byproduct, and this is, by scaling up, will be one of the risks. The other risk, as I see it, although we reach now high efficiency, high Faradaic efficiency in the sodium reclamation, we need to understand that during the scaling up, it still remains with high efficiency, high Faradaic efficiency, because the sodium recovery is crucial to the economics of this technology.
Jeremy?
So, how important is the sizing of the material? I would think that in order to get more reaction, it helps if things are finer, but also if the material is finer, when you mix the sodium with the iron oxide, it means it's more difficult to control the reaction, as you said. Then you can have a runaway reaction and some byproduct streams. So how critical is that whole part of it?
Yeah, particle size.
Yeah.
We evaluated at this stage up to 10 millimeters particle size, and we evaluated, we demonstrated that there is no difference, meaning tailings, for example, are a really fine powder, and we also started with run-of-mine material, which we grinded up to 10 millimeters, and the kinetic model shows that there is no difference in this range. What will happen in a bigger particle size, it's a question, and of course, once we will scale up even further to ton per day production, we will be able, in the unit itself, to have an input that is bigger than 10 millimeters. So it's all about the mixing process, sequence of the addition of the material during the process, and controlling the temperature, as you said.
Okay, but the morphology of the iron ore is going to have an impact. That's why we can't take any iron ore and upgrade it to DR grade. So some ores, no matter how much you grind them, you can't concentrate it any further.
Yeah.
And so as a result, what that means is that some of the iron is so tightly bound to some of the gangue material that it's very difficult to get actual contact. So how do you complete the reaction?
That would have been my question as well.
Yeah.
Is it because sodium likes oxygen more, or only the oxygen that is bound to iron? Because you are able to extract iron from so many different types.
Yeah, from different compositions.
What's the mystery? What's the magic there? That why is it so?
Yeah, so it's actually because sodium is such a strong reactive and reactively really fast, so it can be bonded or can be, let's say, with the mechanism gives the electrons to the iron oxide really quickly. Thermodynamically, it's really stable. So even slag that has different phases with iron, such as manganese and stuff like that, we still extract the iron from it. So it's a good question about the mechanism, but thermodynamically, we've evaluated that this is the case.
So it's not elemental iron. It has something to do with the oxidative form.
I assume, yeah.
Yeah.
I assume.
Yeah, but presumably you just look at the oxide stability diagram and you can say what's going to react with what.
Yeah, so actually there is no phase diagram.
Well,
and we've conducted...
the oxide stability diagram, the Ellingham diagram, is
Yeah,
not a phase diagram.
Yeah.
It actually shows the propensity for different things to displace one another in terms of the reaction. It's the oxygen potential of the different compounds. But anyway, okay, well, we'll come back to that in a couple of years. I'll probably ask you the same question after you do your first scale-up. So.
I hope that it will be much stable.
There is another question, just one row behind.
Have you analyzed the possibility of contamination of the steel, of the iron with the sodium? Let's say, how much sodium you can lose with the product?
In the product or during the recovery of it?
In the product, together with the iron.
Yeah, so we evaluated that with the chemical separation that we are doing, sodium that is still with the iron extract with the chemical separation. And because that after the chemical separation, we insert the chemical that we are using, which is sodium hydroxide, straight into the electrochemical cell, then we recover the sodium back. And our goal is to reach, in the iron itself, below 0.2% of sodium.
0.2, okay. I have one of these tablets, so I bet they don't taste saltish.
They're not what?
They're not saltish. So you have taken everything out, all the sodium.
Yeah.
Okay. There was one question, and that's the last one.
Thank you for your kind of excellent presentation.
Thank you.
How do you expect what the reactor looks like? Is it only mixer or maybe some intensive mixer or something like that?
The reduction step
Yeah, reduction
is a
step.
stir tank reactor, a pressure vessel stir tank reactor.
Steel tank.
Yeah.
Continuously operated steel tank reactors.
Yeah, because it's a very fast reaction.
Okay, thank you.
Thank you. That will be all.
Thank you so much.
Thank you.